Hello, today I'll be talking about temperature and reaction rates for Module 14. Take a moment to familiarize yourself with the basic equations and general formulas for reactions. In order to explain why the reaction rate changes when the temperature increases or decreases, we need to understand the mechanisms at play. The first theory I will talk about is the collision theory, as it explains why different reactions occur at different rates. For any chemical reaction, reacting particles must collide with each other. However, particles can also collide without a reaction occurring. There are three main criteria that must be satisfied for collision. 1, a collision. 2, sufficient energy present. And 3, proper orientation of the molecules. Molecules collide in order to form products, and they need to interact with new molecules to form a collision. If a collision occurs and all molecules interact, then they can be classified as a first order but still require sufficient kinetic energy to generate bond destruction. A sufficient energy presence is required to cause the interatomic bonds to stretch and bend, breaking their potential energy within species, which will make them more easily to break. As these bonds absorb more energy, they will shift to a higher quantized vibrational state where their bonds will weaken. And the third criteria is proper orientation of molecules, which allows the bonds to split more easily. If the bonds don't split, they become distorted or twisted in order to react with a different molecule. The rate of reaction influences one of the following or a few: frequency of collision, effective collision regarding either sufficient energy presence, or effective collision regarding proper orientation of the molecules. A reaction mechanism is the rate of change in concentration of reactants with products over time. A mechanism is an overall sequence of singular or multiple elementary reactions. An elementary reaction involves a molecular event of 1, 2, sometimes 3 atoms, molecules, or ions that significantly alter a molecule's energy or geometry, or it also produces a new molecule. An intermediate in the reaction is a species that does not appear in the balanced equation, but helps reach the overall reaction. The molecularity is the number of molecules that collide during elementary reaction or mechanism, and the rate determining step provides an experimentally determined rate law for overall reaction. With our knowledge of the collision theory and reaction mechanisms, we can apply them to Arrhenius equation. The Arrhenius equation is another form of exponential decay, and the exponent is a ratio of activation energy to average kinetic energy. The equation uses the chemical reaction constant K, the pre-exponential factor A, active energy EA, gas constant R, and the absolute temperature of reaction time K. For these relationships, we know that as the rate constant of reaction increases exponentially, then the activation energy decreases, as well as a small activation energy does not require as much energy to reach a transition state, thus allowing it to react faster than a reaction with higher activation energy. In addition, the rate of an uncatalyzed reaction will be more affected by temperature increase than a catalyzed reaction because of uncatalyzed reaction begins with a lower activation energy. The transition state theory provides a more accurate suggestion to Arrhenius equation and the collision theory. There are 3 major factors to consider when satisfying a molecule undergoing a transition state. The first is the concentration of the activated complex. The second is the rate at which the activated breaks apart. And the third is the way the activated complex breaks with respect to reforming reactants or to form a new complex. There are 2 potential outcomes. The first is to return to the reactants, and the second is to rearrange bonds to form products. This theory contains a flaw, as in a solution, non-equilibrium solution can arise. However, using other theories, we can correct these discrepancies. Transition state theory is very useful to calculate thermodynamic properties from overall reaction rate and is very useful in medicinal chemistry. The real-life example I will use is tempering chocolate. Tempering refers to the heating and cooling of a metal to improve its properties such as consistency, durability, or hardness. Tempering involves manipulating the crystal structure of cacao powder in its 6 polymorphic crystals. When chocolate turns to liquid, there are no crystal structures present, and the type 5 crystal structure are destabilized and detached from its bonds, making it the most ideal state. The steps involve melting the chocolate by heating in order to destroy all crystal forms, cooling the chocolate precisely, holding the temperature just below where the crystals are formed, typically below 35 degrees Celsius, then to warm it up in order to eliminate any bad crystals formed for remelting so that only the desired crystals form again. The chocolate cools, which causes the seed crystals to help speed up kinetics to form the V structure. The thickened chocolate indicates an adequate number of crystals formed, and if the temperature goes below, then the chocolate will solidify and becomes useless for working. Now, the chocolate must sit for a while in order to ensure it's fully crystallized. This process can take up to 3 to 4 weeks, depending on the industrial state. There are multiple ways of tempering chocolate, such as the traditional way up on stone slab, at home, in a factory with tempering chocolate, or in a lab. As we can see, temperature plays a key role in tempering chocolate as it manipulates changes in the rate of reaction to reach a desired state. Here's a sample problem. Find the rate constant if temperature is 300 Kelvin, activation energy is 150 kilojoules per mole, and the pre-exponential factor is 10 m to the negative 1 s to the negative 1. Here we are using the rate of reaction equation. We take the logarithm of both sides, sub in the values, take the exponent of E to find K. Here is another practice problem. Find the new temperature if the rate constant at said temperature is 10 m to the negative 1 s to the negative 1, while the temperature at 200 Kelvin has a rate constant of m negative 1, s negative 1, and the activation energy is 400 kilojoules per mole. We are using the logarithmic function of rate of reaction with respect to 2 different temperatures, solving by putting in the known values into the equation and finding T.